thank you, Hoyt, for accepting our invitation, and thank you for the audience coming to this talk. Hoyt Kesterson is a senior security and risk architect with Avertium in Phoenix, Arizona. He has more than 40 years of experience in information security, and for more than 20 years, he chaired the international standards group that created the X509 digital signature certificate, which is a fundamental part of TLS. He is also co-chairing the Information Security Committee in the ABA section of Science and Technology Law. He's also a testifying expert. And as Donna said, today he's gonna talk about passwords. And I'm gonna let Hoyt start his presentation.
Okay, so we went through this once before, so let's see if I can actually do it right this time. All right, down one. So that says that's going on. Okay. Zoom notification. And now I go to PowerPoint. And if everything's working well, you're seeing slides. Is that correct?
Yep.
Yeah.
And
okay,
I might also mention we're recording this.
Yeah. Well, yes. I've been informed this by email a few days ago. So I have no problem with this. Okay.
Good. Okay. Great.
So,
thanks.
as it's been said, my name is Hoyt Kesterson, and I've been doing security. I actually say 40 years because if I say any more time than that, you think I'm really ancient. But literally, almost about the time that multiple people started connecting in with computers, I was there, and so involved with how in the world do we actually secure these things. And in reality, my interest isn't security. It wasn't security. My interest was distributed applications. So almost very early days, right after Sutherland had done his experiment with computer graphics, the Air Force gave me these really expensive graphic terminals. And I got interested in this problem about how I could use kind of like a mainframe, a regular computer, and this graphics computer, and have some of the parts of the problem here, some of the problems there. And then I went into open systems interconnection, and I was in that international standards group working on a lot of things which you may hate, like abstract syntax notation 1. And so I chaired the group that ran the presentation layer for OSI, and I worked on a bunch of things. And one of the things that became very clear to me in terms of distributed applications is that you have to secure them, okay? And for shared systems for the longest time, we've come up with this concept of, you know, there's an identity, and then how do you authenticate yourself? And it's been by a password, which Nist recently called in the standard memorized secrets. And so people have asked me, well, this seems like a mundane topic. What you worked on much more esoteric things than this. Why do you keep talking about passwords? It's because if you take a look at everything that happens, ransomware, breaches, you know, so forth along that line, a large majority begin with a compromise of credentials. And so it's like our weakest link. And so how do we fix that? And this has been a topic of interest of mine for some time. In this particular case, I'm going to go more along the line of storage, about how you have to store and save passwords. And I was mentioning just earlier today that this didn't really become a problem until we actually went to that concept of time sharing a long time ago. Because it used to be you had a computer and you were the only person using it, whether it be a PC or a large mainframe, how it kind of worked. You were the only person on it. So there was not this question of who are you. You kind of brought all your materials, all your files, all your disks, all your tapes. If you were using tapes, all your punch cards, if you were using punch cards. But the minute we started sharing systems, we had to actually start identifying and allocating resources based on identity. And we ran into this issue of basically, you just can't trust people if they assert identity. that they're who they say they are. So we make them authenticate themselves. And we've been doing that with passwords. So my question then is, this talk starts out, talks about cryptocurrency. What does cryptocurrency and protecting stored passwords have in common? Cryptocurrency mining, of course, as people know, is this process where you're out there basically doing this phenomenally energy wasting work, trying to gain control of ledgers, which we'll talk more about. And then if you do, you get awarded cryptocurrency, coins, and hence the term mining. But the concept they have in common is hashing. So you guys are all computer types. You should know what hashing is, but just in case, we'll do a little review. So a hash function basically kind of crunches everything together. It crunches could be a very large collection of bits or whatever to make a much smaller fixed string of bits, okay? Now, one characteristic of this is the fact that you really can't predict what's going on. So for instance, if you had a large video, okay, or an Encyclopedia Britannica or anything else on this line, you hashed it, and then you went and you changed one character of it, and you hashed it again, you would find the second hash is wildly different, unpredictably different, okay? And this is in fact how we do integrity mechanisms. We basically, rather than comparing large files to each other to see if they change, we compare the hashes of large files with each other to see if they've changed or if they're the same. So cryptographic hashing, I mean, hashing is used in a lot of things, indexing for databases and so forth. But for cryptographic functions, we have some certain considerations. Number one, you can't extract the original content from a hash. That's actually, to me, pretty obvious. If I take the Encyclopedia Britannica and take it to 180 bits or something like that, I really don't think I've invented the world's best compression scheme. I'm not going to be able to extract the encyclopedia back out of it. But there's also a point of cryptographic sturdiness or hardening, where basically the hash can't really give a hint of the content that went into it. And that's when you take a look at earlier hash functions, message digest 1 and so forth along that line. That's a weakness that was found, where basically someone would say, well, I can demonstrate that I can tell you what the first 2 bits of the content that went into this hash were. And the minute someone's done that, they say, oh, well, it's just a little bit of work to do some more. So the second thing is that you can't create 2 sets of data that will hash to the same result, okay? This is called collision resistance. And this is extremely important in the world of digital signatures. It would not be a good idea if I digitally sign something, which is really just nothing more than an asymmetric encryption of a hash. If someone could actually say, well, here's something, and here's this hash, and here's the signature, but I can actually modify this something in such a way that it'll generate the same hash and therefore fool the signature. So you have to have collision resistance. And then the second item sounds first off like it's the same thing, but it's given a hash, you can't create data that would generate it. And that's called a pre-image resistance. And that's basically saying, here's a hash. Can I figure out some file that would generate that hash, even though I don't know what originally caused it? So these become 2 fundamental concepts. They're used in integrity mechanisms everywhere, and integrity to detect change. I keep insisting, hash functions don't prevent change. They only allow you to detect it. You need other mechanisms to stop it. So Nist has several hash algorithms. Of course, there's SHA-1, but some weaknesses were found in it. So the ones we look at now are SHA-2 and SHA-3. SHA meaning secure hash algorithm. And then, as I mentioned, a digital signature is nothing more than taking a hash and then using an asymmetric algorithm like RSA or Diffie-Hellman, elliptic curve, anything else of this nature, and encrypting that hash. Because you keep the message in the clear, but you encrypt the hash, and what you're doing is you're giving some integrity, source integrity, and data integrity, and for digital signature. Okay, so now we go back to this problem of where I've got a system and I want to basically store passwords, because Bill's going to connect, Mary's going to connect, Jane's going to connect, Ralph is going to connect. and each of them are going to assert their identity as Bill, Jane, Mary, or Ralph, and they're going to then enter a password to prove that they are that person. Well, it would not really be a good idea if I just stored the passwords in the clear, because systems that get broken into means that you can exfiltrate those passwords and you can pretend to be, you know, Bill, Jane, Mary, or Ralph. So it's not a good idea to store them in plain text. Encryption is not a good idea. Well, why is it not a good idea? Well, clearly, if you encrypt something and someone exfiltrates it, as long as they don't get the key, okay, then they can't how do you want to say it? They can't figure out what the password is. But one of the basic problems is that you, as the owner running of the system, the holders of the key, have access to it. So what you'd like to do is, if you have a system where you're using authentication to come in and something gets compromised, you'd like to prove that you, as the owner of that system, had no clue what the password of this person was, and therefore you couldn't compromise it. With encryption, of course, since you have the key, you can compromise it. So that's not a good idea. It's reversible. Plus, if someone, while exfiltrating the encrypted passwords, also gets the key, then everything is lost. Okay. So there's a much better solution. We really want to basically store a hash of a password when it's first created. So I'm Bill. I come in and I want to make a password: all dogs go to heaven. Right. So I would give you all dogs go to heaven. You as the person I want to connect with, and then what I would do is I would store that hash. Now later, when Bill comes in again and he enters his password, all dogs go to heaven, then as a receiver of that, I would hash it. And then I would compare the two. And if the hashes are identical, then the inputs are identical and the password's doing. The interesting thing is that since all I have is the hash and all I've saved, is I really don't know what the password is. Okay. So effectively, I can authenticate it without really knowing the value. And at no point do I convert it back to a password. So there's no exposure there. So that doesn't become an issue. And that's really the best way to kind of do this thing. So basically, connect password with receipt. Okay, so let's go to something called hash chain. Now, hashing is really fascinating. It's been around for a long time. And back in, 68 or something along this line, it's in my notes, a couple of guys at Bell Labs, Bell Corps, came up with this idea of building a hash chain to actually use as a timestamp. And so the idea would be is that if you wanted to prove that some document, some string of bits, some whatever, you know, some digital thing, it could even be an image, you know, existed at that time, okay, not when it was created, but at that point that it existed, you would actually hash it, and then you would take that hash and roll it into the hash chain, and this would just go. People would just kind of accumulate, roll hash of hashes of hashes of hashes, and then their mechanism of recording the very top hash, okay, because you want something that is definitive and trusted and public, is they would actually have an ad in the classified in the New York Times, okay, and you could actually go back and look at it, and it'd be this little strange collection of characters representing that top level hash, and it would, of course, naturally, your granularity is only a day, so that mechanism couldn't exist forever. But at that time, for a lot of people, that was good enough. You know, it's almost like the bit about mailing a letter with a postmark on it, which is how people used to actually prove that, for instance, in terms of patent technology, that something was timestamped. And so this actually became a company called Surety, and it actually still exists. Obviously, they've had to change the technique a little because you need granularity much finer than a day. But essentially, it is really nothing more than a chain of hashes. Now, along came this thing about a requirement for a ledger. And this is in terms of cryptocurrency. So what's the problem of cryptocurrency? The problem of cryptocurrency is not people perhaps, how do you want to say, counterfeiting, because you can use digital signature schemes to basically establish provenance of cryptocurrency. The problem is you can spend it multiple times. So Bill can send something to Mary, send $100 of crypto coins to Mary, and then later send 100 crypto dollars, same cryptocurrency to Bill, and I mean to Ralph. How do you know? Okay, so the idea they came up with it was that, gee, what I'll do is in this ledger, okay, I'll actually record a transaction, okay, that Bill transferred these 100 crypto dollars to Mary. And Mary can say, okay, she can see that record because it's a generally used available ledger, and she can say, okay, the transaction really happened. She now has that money, and of course, naturally, I transfer the currency to her. And then later, however, if I were to transfer it to Ralph, try to spend that same money with Ralph, he'd be looking at that same ledger, and he said, well, you can't send that money to me. You've already sent it to someone else. And so essentially, that's kind of why all of a sudden with cryptocurrency, this need to basically have this general ledger, a correct general ledger, grew in pressure. Now, these things, as I mentioned, were digitally signed to establish provenance, but what am I doing to link everything in? This is a hash chain, and who's the authority, right? So the hash chain that I mentioned at the very beginning, Surety, there was one authority, that was Surety. It's the one that controlled the hash chain, did everything together, and said, here's the top of it, and you knew who was doing it. Well, when Bitcoin was done, the guy who did Bitcoin really wanted to basically say, hey, for whatever reason, I have no idea why this is, for whatever reason, I do not want governments involved with this, okay? I would So effectively, he came up with this mechanism, building this good stuff of more data. So essentially, a bunch of people, 100,000 entities, all of them are trying to basically build this next block. And everyone who's doing any cryptocurrency transfers, actions, and wants stuff put in a ledger, sends it out, and all these people pick it up. And then they're sitting there and they're putting it in the block, and they're actually computing a hash to link it into the hash chain. Okay, well that sounds pretty easy. Why isn't just everybody doing the same thing? Well, okay, so there are cryptocurrency models, there are blockchain models which are more authority driven, but in this particular case, it's not done that way at all. It's basically, you're going to take this hash that I'm doing, but I'm going to make it difficult. And I'm going to have this thing called proof of work. And this is done by the people who are essentially, quote, responsible for BitChain. They're Bitcoin. They're really trying to make it so that it takes about 10 minutes to generate a block, so to speak. That's what they like to see. And the way they do this is they create something called a proof of work. Okay, so a proof of work. What's the proof of work? Well, the way they do it is they basically talk about you have to have so many preceding zeros in the hash value, right? So remember the pre-image problem? I can't take a look at a hash and basically decide that this is what I can do. There's no real shortcut to basically saying, well, if the first 30 bits of this hash chain have to be 0, how do I get that? I can't. The only way I can get that is to basically hash. And therefore, I must be able to put a variance into it that allows me to get different hash values. This is called a nonce. And so what I do is I plug a value in there and I hash everything. And I come up with a hash value and I look at it and say, does it match the proof of work? Does it have enough leading zeros in it that the proof of work required? And if it doesn't, then I change the nonce and I do it again. And then I do it again. And meanwhile, there are a bunch of other people, entities, who are doing the exact same thing. They're all competing to be able to establish the hash for this block. It is, in fact, a technical free-for-all. It's consuming a lot of electricity, very wasteful electricity, because sooner or later, because you have all these people doing all these calculations, but only one winner. Sooner or later, someone will actually come up with a hash that matches the criteria, the proof of work. And when they do, they win, okay? They get to basically put that hash value in as the hash value for this block, so representing the cumulative hashes that came up from preceding blocks, plus the data that's in this block, and they've now got it done. And then everyone else who's been working, they just throw everything away. In fact, you've done trillions of hashes, trillions and trillions and trillions of hashes because multiple people are doing them, and most of them are thrown away because they don't meet the criteria. You finally only have, there can be only one, okay? And so it does it, and it goes on. And so then what we end up with is essentially start it all over again from the next block. So what does this mean? It means that when cryptocurrency first started out, people would be like running this stuff in their PCs. And in fact, one of the interesting things that still happens at some places, they have to worry about people who kind of like installed hidden software in their system, computing hash values. Very much like that thing you used to be able to volunteer for, SETI, Search for Intelligence Life, the intelligence, extraterrestrial intelligence. The idea was they wanted a bunch of people decoding as much as possible, and you voluntarily put this stuff in and kind of distribute it out. So you ended up with a bunch of parallel processes. Okay, so if you're going to do crypto mining, it becomes very clear that the only way you're going to win, unless it's luck, okay, there can be luck. A PC could actually come up with and generate this just out of luck. But if you really want to make a paying business, you got to have better odds than that. And you do that by basically, you need special hardware, right? So anyone who's in the cryptocurrency nowadays, and this is what tickles me, because even though the people who created this, whoever this person was, okay, it was his idea that he wanted a free, currency from an authority, has essentially just moved it to, well, really, the only people who can really successfully compete in cryptocurrency right now are people who can afford to mount large numbers of servers generating much heat, which is why Iceland's a popular place to keep them, and generating trillions and trillions of hashes to try to solve this problem I just told you. So the entire goal of authority seems to not be winning, because it seems to be settling down to only a few entities that will actually have the wherewithal to actually do this computation. But the interesting thing is that to do this, they, as I said, generated this special hardware. Now, the thing is that you can go and you can find, and you can see here that I can go out and buy at not too outrageous prices machines that will do, and here's the interesting thing, it's a new unit of measure. It's THS, trillion hashes per second. So if you look at this, you see something that does 110 trillion hashes, 112, 50, 73. And notice also that they talk about the amount of power that they consume, but the prices aren't that outrageous. I mean, not at all. If you really wanted to do a lot of hashes, even if you weren't in the cryptocurrency business, you could spend the money for doing this kind of thing. And you're doing, like I said, perhaps 110 trillion hashes a second, okay? Even though you're burning a lot of electricity. And that's the interesting thing. Think about people in the cryptocurrency bill, how many, they have hundreds and hundreds of these systems. But think about how much electricity they're using. So anyway, excuse me, move this back to where it's supposed to be. I hate it when I do that. There we go. So let's go now to attacking stored passwords. And there are two ways to do this. There are online attacks. And online attacks means you're actually connecting to the system. And you're actually saying, okay, here's Bill's user ID. Here's a password, I'm going to try it. Here's a password, I'm going to try it. And you typically try to use popular passwords. And it's unfortunate that this works, but it does. I think it's interesting that when you see a lot of attacks that are ransomware attacks, and they talk about how they breached the system because they came through RDP, the Remote Desktop Protocol. This always tickles me, because Remote Desktop Protocol is not set by passwords set by general users. They're passwords set by admins. So even admins aren't doing this right, okay? And they're supposed to know what they're doing. So we have people who use passwords, 1, 2, 3, 4, 5, and all this other good stuff. So there are these dictionaries of passwords, plus people have gone out and broken into systems and extracted passwords with these compromised lists. The only defense against this, it's fairly effective in certain ways, is that typically you should be basically saying, if you try to password and try to password and try to password, I'm going to lock your system. I'm going to cause an alert. You're going to have to wait maybe a half an hour for it to unlock, or you're going to have to call tech support. So you kind of know that someone's trying to attack this system. Now, to kind of get around that, there's this thing now called password spraying. It's kind of attack. I like to refer to it as low and slow, because often you really just want any account. You'll work from there. You're just trying to find any account on and maybe on any system. And so you try a few passwords and then you go away. You try a few passwords somewhere else and you go away. You try a few passwords somewhere else, and you come back much later and you try it again with another set of passwords. So you finally get something that works. And the only thing that would catch something like this is something that is doing an analysis of everything that's happening in your environment. Okay. And even then sometimes, because sometimes they don't care necessarily. Maybe an enterprise isn't targeted. They're looking for any low-hanging fruit. And these are the online attacks. I don't care too much. I'm not too worried about online attacks because I think there are various ways in which they can be handled. But offline attacks are insidious, okay? So the point is you exfiltrate a hash. Now, you would think, well, isn't that difficult? Well, no, it's not difficult. There have been versions of Windows PC software for purposes of local authentication where the hash is actually stored on that system, right? And my company one time, when we were doing some penetration tests, went to a PC that was in the lobby of a pretty big company. They had the stuff there for people to basically file for job entry, job so forth, and just sit down and put a flash drive in it, extracted information, in particular extracted the hashes that were there, not that difficult to do. And it just so happened that system had been recently visited by an admin who actually went and logged into it. So now we had a hash of a password of an admin. It didn't take us long to break that hash because that was Microsoft back in the days when it used to break hashes into 7 characters of hash. Microsoft didn't quite understand what hashing was all about. They've much improved, but back then, and so all of a sudden we had, basically but people break into systems. They come in any other way and they do it. Now, every now and then I then see news articles where someone say, well, they broke the hash. Well, no, they've never broken hashes because number one, you can't really reverse it and get the information out of it, right? So what's really happening? Well, what happens is that you basically say, well, I don't know what this password is, but I know what a lot of possible passwords are. So what I'll do is I'll hash them, and then I'll compare those hash values to the stored values. And if there's a match, then I know what the password is, okay? And you could go back 10 years easily, 15 possibly, and you could actually buy CDs, DVDs, whatever else, these files of maybe every 8-character alphanumeric password, and you do this good stuff. And so these pre-computed hashes, so to speak. So someone said, well, what do we do about that? Well, what we do is we will actually salt the password. And salting is nothing more than taking an extra string of characters and appending it to the password and then hashing. It's like you're making a variance of it. And if you're lackadaisical, you're essentially doing one salt, maybe for your system, or maybe even for your enterprise. This is not a very good idea. Someone figures out what the salt is, because salts are not a secret, okay? Then effectively, the best way to do it is to actually make the salt unique to the account that the password is for. And the advantage of that is that if multiple users within your system inadvertently choose the same password, which is possible, right? It's the birthday problem. Then you don't end up with identical hashes, and there's no hint that 2 people might have the exact same password by looking and finding identical hashes. So that's what the salt is. So this is a defense, all right? And this defense held for a good while. Okay, so there are a couple of standards that I'm going to mention one of which probably at this university isn't all that well known. I don't really know. That's the PCI data security standard. I like the PCI data security standard because it's pretty prescriptive rather than frameworky advice that says do this, okay? So in this particular case, it says use strong cryptography, okay, which it defines elsewhere. It render all authentication credentials, passwords, phrases, unreadable during both transmission and storage on all system components. Can't read them. Now, it doesn't tell you exactly what mechanism you're using, but it is supposed to be strong cryptography. So, you know, you're not doing base 64 encoding or something like that, or having CISA ciphers. So the other one is Nist. Now, Nist had standards dating back to the early 2000s, which had all kinds of password advice, which has significantly changed. And so I actually recommend that if you get a chance, you take a look at these 4-part document. But in this particular case, we're interested in B, Digital Identity Guidelines from 2017. And it has a line there called verifiers. Verifiers, meaning the people who are checking passwords, shall store memorized secrets in a form that is resistant to offline attack. And notice they're actually saying offline, because they know the concern is effectively someone just generating hashes against it. So that's what the two standards say. What are people doing out there? Well, people are doing different ways to do passwords securely. And so one way is that they like to talk about is the password-based key derivation function to PDKDF2. You've heard of this. And so it basically says you need to take a password, then you need a salt, which needs to at least be 32 bits long. You need to have an approved hash function, SHA, and a cost factor. And then what you end up with is a hash. What's the cost factor? With iteration. And that's been the defense for some time in terms of making things stronger. So basically, you don't just hash a password, you hash it, and then you hash it again, and then you hash it again, and then you hash it again, and you hash it, maybe 10,000 times. Well, what's the concern here? Well, you don't want to hash, someone said, well, okay, let's just hash it 1,000,000 times. Well, that sounds like a great idea, but unfortunately, a user has just entered their password, and they would like to know whether they're accepted or not, probably within a few seconds. And particularly if they've made an error, have to type it in again. They're not going to really want to. They're not really going to want to wait a minute and then say, okay, well, you have an error in your password. Try it again. Okay. So there's an upper limit you can put into your system where you have to be certain that you're not really irritating your users. Users don't like to be irritated. They stop using your system. So Nist also believes, okay, and this is an interesting one in my opinion, that if you take a password and you hash it with an appropriately sized salt that's kept secret on an HSM, that will resist attack, just period. So think about that. Salts aren't secret. Someone's exfiltrating your password somewhere right along with that hash, password hash. Somewhere right there along with it is the salt. So they learn the salt. The salt is not a secret. I mean, it can't be a secret because you as the verifier have to have that salt when someone sends you a password to append that salt to it, to hash it, and then so you can do the comparison. So you have to know what the salt is. So, but Nist says, hey, if you can put this thing up in an HSM where people can't get to that salt. Now, this is tricky because HSMs typically are very primitive. So if you're actually just using it as storage, you put it up there and then you pull the salt back out, it kind of slows you down a bit, but also at the same time, the salt becomes exposed. And if the salt becomes exposed and someone's there sniffing, scraping memory or whatever else, then they can get it. So you really want the computation done in the HSM. The basic problem is that HSMs are fairly generalized products. There's the payment card industry has a really interesting problem in the fact that often I have two encryption regimes. I might have an encryption regime between my point of sale terminals and the system that's aggregating, collecting them, and a different encryption regime with the people who are going to process it, the acquirers. And so I will actually have one key being used to encrypt the data, say on the keypad. That's the best when the card is swiped, and then that sends it to some point within your enterprise, and then it's time for you at the enterprise level to go and ship it off to a processor, but that processor is under a different encryption regime, so it's a different encryption key. So what do you have to do? You have to decrypt your thing, so the keys and so the credit card numbers in the clear for a bit, and then you re-encrypt it, right? So even if you use HSMs, please decrypt this with a key that's in the HSM, and then later recrypt it. I still have to bring that key into the clear to do it. So there are things which are called payment Hsm. And what's the difference in a payment HSM? It's an HSM whose set of functions has been extended to have a function which will allow you to take a value that's encrypted under one regime key and decrypt it and re-encrypt it all within the HSM and send it out. So I believe that if we're going to do this Nist kind of thing, seems like it'd be a good project. I really don't want the salt value to come out. I want that to be done there. But gee, I don't want to go there and do all these iterations and stuff. So there might be a balance. It might well be that all I really have to do is send the password to it the very first time, have the salt appended to it, have one hash done, or two or three or four, whatever else, then send it back, and then repeat the hashes outside. Okay, so effectively you have a better attack. It could be some interesting study in this area. No one's really done anything because HSMs typically either do encryption for you or they store values for you like keys. Okay, so the whole problem then is that PBKDF2 is just not enough nowadays. And why? Well, you have to blame ASICs. ASICs, application specific. Okay, so we'll get to that. So password implementation, password protection, password everything. It's just bizarre how people don't seem to do this right. So you can see here, this was an ad from Krebs where Facebook stored hundreds of millions of user passwords in plain text for years. Now, everyone saw the movie about the start of Facebook. He even had these coding tests. These are supposed to be pretty bright coders, but it seems pretty bright coders don't necessarily know how to do things securely. It's like this additional skill set, that you, and interestingly enough, not everyone can learn it because some of it's a little bit mathematics based. So, well, is this just a problem with Facebook? No, it's a problem with everyone. So in 2019, University of Bonn did this really interesting study. They basically said, let's talk about password protection. And they went out. Now the sample's way small, right? But they went out and hired good, well-trained freelance Java developers, and they basically said, what we'd really like you to do is we want you to write this application. It's a fairly simple application, and however we want you to authenticate the user. So you're going to need to collect the passwords, right? So they took 18 of them and said, make sure that you protect the password. And the others, they said they didn't say anything to. Okay. Of the 18 who were not prompted to do secure passwords, so 18 were not prompted, and the remaining of the 43, which would be 25 were told we need to secure it. Of those that were not told anything about passwords, other than the fact they had them, they actually just stored the passwords in plain text. That's what they did. Okay? 3 of the prompted group, even though they were told to protect passwords, still stored in plain text. So right now you've got over 40% of the population who just basically didn't think it was that important to protect the password. And these are supposed to be experienced programmers. And this is 2019, folks. So and those who did choose to protect it, they did interviews of all these people, and they seemed to be very confused. There was a confusion between scrambling characters and encryption and hashing, okay? And so we found people who were using base 64 encoding. You know what that is? That's how you just lop off some bits to handle binary in a character format. And MD5, now this system called out the use of MD5 I'm not so upset about MD5. MD5 has collision problems, but I'm not really quite certain collision problems inhibit a crypto thing. But no matter what, MD5 is deprecated, so you shouldn't be using it. Okay. Only 15 people salted. Okay, and that's the people who were told to do it. And only 12 used bcrypt or PVKDF2. Okay, and those who did, 5 set the iteration to over 10, and 16 set it to 1. Okay, so by setting it to 1, it means they just didn't set it at all. So effectively, it just hashed once. So what's all this show? It basically shows that programmers, normal, regular programmers, really aren't good people to do security, because they're not taught this for whatever reason. So you have to take some caution. As I said, you know, it's a very small sample set, but I actually considered it fairly indicative. They first actually ran the test against students, and it showed pretty much kind of the same thing. But hey, you'd say, well, these are just students. Well, no, they went out and they found people who were experienced programmers who sold their skills as freelance, and these were supposed to be good programmers, and yet they still did it all wrong. So people aren't doing programming correctly. It's an issue. Now, the other problem is the specialized processors. Remember I told you need special processors to do things? And there are several different kinds. There are graphics processing GPUs, application-specific integrated circuits, ASICs, and field programmable gate arrays, FPGAs. And the problem is these things are, because they're specialized, they're much faster than authenticating servers. You saw that I was pointing out to you these ASIC systems for mining that are sold that are doing trillions of hashes per second. ASICs, if you take a look at it, what is it? It's on the die. It's a processor that pretty much does one thing: SHA-3s, and it does SHA really well, SHA-56 or whatever, really quickly. Doesn't do anything else, but that really means that I can make up a pretty small die, pretty small processor, and make it fairly inexpensive to make something that does this one thing very well, whereas your general processing computer has to hash amongst the millions of other things it has to do. So the bcrypt, PVKDF2, both of them, to defend against this offline attack, have been using iteration, but it doesn't work. I mean, as I've mentioned, I can go ahead and go to 1 million iterations, but it makes it really difficult in terms of my own users. And the attacker can also do 1 million, but the attacker has a significant relative cost advantage because he's using specialized processors to do hashing, like that trillion hash type thing I was showing you. So effectively, this is not good. So here's what we know: that mining technology, which you can acquire, will speed the process of generating hashes of very large password dictionaries coupled with an exposed salt. So what am I going to do? If I actually go and I exfiltrate information from a system, I'm going to get the hash and I'm going to get the salt. And I'll probably even get a clue by looking at the code of what the iteration is, how many times it's being called for iterating. And now I can set this problem in my mining software, and I can run very large password dictionaries. I mean, it doesn't have to be like just the common ones like password and 1, 2, 3, 4, 5, 6, 7. I can use the uncommon ones, you know, and I can be very specific to it by the fact that I can generate these exposed salts. It may take me a while, but if I can do 110 trillion hashes a second for a very small amount of money, relative amount of money, then all of a sudden it becomes really worthwhile. And don't forget what's happening out in the world out there. Okay, I was interviewed recently for someone, and I was talking about ransomware, and I was talking about how what we've seen is capitalistic practices, okay, happening in the crime world. People are specializing, so you might actually have people who compromise or figured out how to compromise the system. They've got compromised credentials, but they aren't attacking it. They'll actually sell this to people who are actually doing ransomware. Okay, and even someone who wants to do ransom may themselves not actually have the stuff that does the ransomware attacks and so forth, they might buy that from somewhere else. So you can actually see a criminal set somewhere saying, well, I'll just set up a small business. I'll buy some ASICs and people can come to me with hashes and salts, and I'll come back at a modest price and tell them this is what I think the password is. I mean, that's the interesting thing. That's capitalism in action right there in the criminal environment. So it's worrisome, okay? So the question then is that hashes like SHA and everything else, one of the criteria when they're selecting them is how fast can this algorithm be? How fast will it run in software? How fast will it run when it's implemented in hardware? And that became part of our selection criteria. We want hashes to be fast, okay? Except when we do passwords, okay? Then we'd like to slow them down. So how do we slow them down, okay? What advantage does a server have, the target, over the attacker who's running these things like ASICs? What advantage do they have? And the advantage they have is memory, okay? Because remember, it's a cost decision. When I'm designing these ASICs and so forth, I'm designing a processor. If I decide to add more things to it, memory caches, L3s, and all this other good stuff, I'm constructing a much more complicated processor, so to speak, and it's going to cost me much more money to do that. And if I change a lot in terms of how that memory is used, then I need to kind of redo that with the ASIC also, because they're not generally programmable type things. That's the whole point of them. So memory is the thing. And we come down to this concept called memory hard hashing. And memory hard hashing has been around for a bit, okay? And the idea being is that in order to compute a hash, you need a lot of memory. You need memory. And if that amount of memory is reduced, okay, then it's not a linear increase in compute time. It's a non-proportional. I want a curve increase in the amount of time I want to do it. And so effectively, I want to have a problem that's intractable enough to resist shortcuts. Now, I'm not going to spend a lot of time talking about that, but if you take a look at the couple that I'll mention, they use memory, and they use memory in a kind of a directed graph kind of way. And they use these approaches called pebbling. So basically, in a memory location, you put a hash, and then the next edge location, you put another hash and a hash and a hash, a hash of a hash of a hash, and you have to go through that process to get where you're going to be, okay? And you have to do it with memory, because if you don't have memory and you're shuffling it out and trying to do things, then your computation time exceeds enough. And there's a lot of really good work. You're in the mathematics department, many of you. So this entire thing about hashing, about directed graphs and pebbling and so forth, this is all combinations. This is all mathematical type stuff, you know. So I kind of wave my hand and say, okay, that's magic. Let's see how that works. And so I do know there's some interesting problems, you know, that people are looking at in terms of like depth reduction and so forth. So some interesting papers are out there. There's probably a lot of good graduate work that can be done in this area. But the idea is to do this, okay? So they had this password competition. Now, there was a competition for AES run by Nist, and there was a competition for SHA, where basically all these people put in these proposals, and then everyone looked at them and see if they could tear them down. And they ran rounds, and they kept reducing the number of candidates until they finally came down to a few, and then they chose them. Now, they ran the program exactly the same way, except this time, rather than being Nist, it was computer security experts. It was people at universities, all running this competition. And in 2015, they basically came up with this Argon2. Okay, so Argon2 was a interesting approach. It used memory hard hashing. It used essentially directed graphs, and the problem, the way you looked at it was in terms of pebbling problem. And so that was that one. Now, Argon2 had several interesting problems. There was something that came up later where people said, well, no, I can do side channel, because Argon2, the first one was kind of like deterministic based on a password. So the same password gave you the same patterns in memory. This was a potential side channel. People could just look at the memory, how memory was being used, and perhaps derive what the password is. So that was, so Argon2 actually came up with several things. It was Argon2D, which is deterministic on the password, and then dependent rather. And then an Argon2I was independent, meaning it didn't use the password to build its graph in memory. And then finally, because that I was open to some forms of timing attacks, space timing attacks, they came up with ID, independent and dependent. And so you do a couple of rounds dependent and final rounds independent. And Argon2 is actually, there's an RFC. Now it's not on the publication track, but the people involved with Argon2 basically are publishing an RFC. It'll be informational, obviously, and they're basically the recommended variant that they say you should be using is Argon2 ID. So let's take a look at a little bit of the history of all this good stuff. You can go all the way back. I was just mentioning that. Back in the days of time sharing, when all of a sudden, for the first time, we had systems which had multiple people on it, and you had to allocate resources properly, you had to authenticate people, you stored passwords. And so there was this guy in Cambridge, in Oxford, who basically came up with this idea. They didn't call it hashing, they called it one-way encryption, basically saying, well, you know, I'm not going to store the password in clear text, I'm going to do this computation. It wasn't the best, but it was certainly really good for what's going on. And then we came along, we started doing key stretching. Key stretching was basically taking a look at passwords and saying, well, I just don't have enough entropy in passwords. What do I got to do to keep on going with that? And then there was the extended key stretching in 1999. Now you really can't find any implementations of this really, because the guy who wrote this, his claim for wanting to write this was he wanted to put these ideas in public domain because everybody was running around patenting everything. If I get this out documented public domain, at least we won't have patent problems. Okay. And then there was scrypt that came out in 2009, and scrypt is did a memory hard problem, but it was really susceptible to side channel attacks. So they wanted to advance beyond that. Scrypt is actually used by Cisco. It's their way in which they protect things in their iOS. Okay, and then I mentioned Argon2, which came out in 2015. Okay, and as I said, there's this RFC you can look at in the 3 versions of it. And then Stanford published a thing in 2016, which is Balloon. And the difference between it, and it uses the memory hard technique also. The memory hard is also this essentially pebbling kind of problem. It's a directed graph thing using memory. And the big difference between it and Argon2, it actually has a formal proof to basically help prove its security, asserted security. Now, Balloon, as I've mentioned, was created at Stanford, right? And if you go and you look at this document, it has a formal proof, as I said. And when you take a look at this document, that says digital identity guidelines, there's no shall with it. It's kind of like saying, you know, you should really look at memory hard hashing. And it gives Balloon as an example. It does not mention Argon2, it just mentions Balloon. Well, why? Well, the reason is because it uses a hash algorithm that's not standardized by Nist. And Nist was not going to mention a hashing algorithm that didn't use SHA-2 or SHA-3. So effectively, Argon2 uses something called Blake. Well, does that mean Blake is a bad hashing algorithm? No. When they did the SHA-3 competitions, remember how they did it in rounds and so forth along that line? When they did that competition, okay, there were some finalists, okay, and one of those finalists was Blake, okay. So, but Blake wasn't chosen. Why? because it was too slow in hardware implementation, slower than the one that was actually chosen. And that's kind of funny considering what we want. We want slow hashing. So Blake, actually a variant, a subsequent evolution of Blake, was used in Argon 2. So we come down to reality. So there are implementations available. You can find a Python for Balloon on GitHub, but Stanford's very clear in saying, hey, this is for research only. Don't go out there and deploy this and then later try to sue us because it turns out to be broken or something. And then there's a reference C implementation of Argon 2 on GitHub. And you can go out and find a few other things too. Like I've mentioned, people have been looking at these directed graphs problems, and there are all kinds of really interesting theoretical attacks against them that could lead to shortcuts. Now these theoretical approaches, these approaches really would still have to be implemented in an ASIC. So it's unclear just exactly how practical some of these attacks are. But if you look, you can actually, there's one from Purdue University, for example, where they basically say, hey, look, here's some minor changes we're proposing to effectively Argon 2, which just changes some of the edge solutions for the directed graphs, which make them much harder to attack. And so you can look at that also. But no matter what, this is something you have to do your own. You're at a university, so it's not so much of an issue to you, but it seems to me this could be something you guys could play around with. And the reason you got to do it, of course, is because evildoers are becoming faster. They're buying these machines, and you got to stay in front of them. And I'll mention one thing to you, which may not be as important, but I mentioned to the people when I gave this talk to the conference that the people who do PCI DSS on, is that the PCI standard allows you to also store sensitive information, a credit card number, as a hash, because you can do several things. I don't know what the credit card number is, but I can tell if this is the credit card number you're proposing. Well, hashes have even worse entropy than passwords. Okay, so these attacks that I just told you that I've done against password files with using these cryptocurrency hardware devices can even be more effective against hashes of credit card numbers or hashes against any PII. So hashes against, for instance, social security numbers and so forth along the line. Anyone who thinks I can protect it this way. And so I give to those people the exact same advice, to basically that I'm giving for passwords. You got to up your game. And that's it. I'm done. So